Electronics at Indian Institute of Technology, Delhi. So at Center for Applied Research in Electronics, we have various areas of research. We have an MTech program in radio frequency design and technology, and we have three core research areas. One is microwave and millimeter wave engineering, including antennas and the current state-of-the-art research. So we have facilities, measurement facilities up to terahertz. Right? So we have a couple of network analyzers up to 110 gigahertz, and there's one at terahertz as well, 1 terahertz as well. We also have a small anechoic chamber for antenna measurements. We have a couple of sources, spectrum analyzers. Then we also have what is known as a probe station up to 110 gigahertz and so on. So this is the facility that we have developed over the years in the field of RF and microwave and millimeter wave engineering. And now we are going to install what is known as a near field antenna measurement system. So the tenders will be out soon, and we'll be having state-of-the-art automated antenna measurement system. So people who are working in the areas of antennas and other RF and microwave engineering components, you are welcome to use our facilities here. And we are you are also welcome to collaborate with us on various topics in this area. The other two areas in CARE are, one is a microelectronics area where a lot of work on sensors, MEMS, then quantum electronics and so on is done. The third area is signal processing, in which mainly we have underwater electronics for Indian Navy, and we also have speech and audio processing, audio signal processing specialized area in CARE. So with this small introduction to Center for Applied Research in Electronics, I will start my talk on human vital sign sensing using radar. So this is the outline of my talk, and as you may expect, my slides are not very fancy. Being an academician, we don't. It's purely an academic presentation based on the work that we have done here. So I'll introduce this vital sign detection. Then we have RCS measurements of RCS is radar cross-section measurement of human subjects. Then respiration rate measurements using vector network analyzer, that is VNA. Then through the wall respiration rate detection of human subject. Then through the wall human subject localization, where the subject is, and respiration detection. And then lastly, we have loss modeling for different material for respiration detection of human subjects. This is very important because the human subject may be buried under concrete or under wood, right, or under glass and so on. So it is very important to model the losses of different materials for this human subject detection. So first, I have put a couple of slides on basic introduction because there may be people from other backgrounds as well. So what is a radar? So radar is basically an electromagnetic system for the detection on location of reflecting objects such as ships, aircrafts, and vehicles. They can operate in darkness because it is electromagnetic signal. So it can operate in darkness, it can operate in fogs, rain, and any environment. So these are essentially used mostly by military people. Right? Say for example, you want to detect if there's any enemy aircraft coming, to attack the country. Right? So these radars are the ones who will detect if it is coming. So they send an electromagnetic pulse. Right? So as it's shown in the figure here, there's a transmitter connected to a transmitting antenna, and there's a receiver connected to a receiving antenna. Right. So the transmitting antenna will send the signal and to the target, and the echo signal that is reflected from the target will be received by a receiving antenna. Right. So based on the received signal, right, based on the received signal and its correlation with the transmitting signal, you can detect from at what distance the target is. Right? You can also detect what is the direction of the target. You can also detect what is the shape of the target and so on. So these are some of the things that electromagnetic radar can do. So normal radar functions are range detection. That is, what is the distance of the target from the transmitting or receiving antennas. So this is range detection is done from delay in the pulse that is occurring, because when the signal starts from this transmitting antenna, it goes to the target and reflects back. Right? So there's a distance that it covers while reaching the target, and when it gets reflected from the target. So based on the delay, right, delay in the received signal with reference to the transmitted signal, right, you can detect what is the range of the target. Then it can also detect velocity from the Doppler frequency shift. So if this target is a moving target, we can detect at what velocity it is moving from the frequency shift that one would get. Then you can also detect angle of the direction of arrival, that is angular direction, right, from the by changing the positions of the transmitting and the receiving antenna, we can detect from what direction, right? The target may be here, it may be somewhere here, or it may be somewhere here. Right? So it is important to detect from what direction the target is coming. Then size of the target. Size of the target is based on the magnitude of the return signal. And then target shape and components. Right? So this is based on what is the return as a function of direction. So based on the material of the target, say for example, if this is an aircraft, right, the reflected signal will be different. Right? Instead of that, let's say it is a military tank, right, which is mostly metal, right, the reflected signal will be different. So based on the reflected signal, right, based on the delay, right, plus based on the positions of the transmitting and receiving antenna, you can detect a lot of things about these targets. So I'll just repeat, you can detect the distance of the target from the transmitting or the receiving antenna. You can also detect from the frequency shift, Doppler frequency shift, the velocity of the target, at what velocity it is moving. You can detect its direction, right? It could be anywhere in free space, right? You can detect what is the direction of the target, right? You can detect the size of the target, and you can also detect the material of the target. What are the different components in the target? One can also come up with the shape of the target as well. So these are some of the things that one can do with electromagnetic radar. The frequencies of the transmitting and the receiving antennas, there are various bands that are used, right? L band, S band, C band, X band, and so on. So a lot of bands, almost all the frequency bands in the electromagnetic spectrum, especially in the microwave and millimeter wave range, are used for this target detection. So Doppler radar theory for vital sign detections. So what are the human vital signs? First is the heartbeat rate. So heartbeat rate is about, the frequency is about 0.8 to 2 hertz, and the chest moves, right, when the heart beats, right, the chest movement is approximately 1 millimeter. So this is what we are trying to detect. So a frequency of 0.8 to 2 hertz and a movement of 1 millimeter. Then respiration rate, the frequencies could be 0.8 hertz, slightly lesser frequencies for respiration rate, and the chest movement due to respiration is about 5 mm. So these are small movements that we are trying to detect. The heartbeat and the respiration cause periodic movement of chest. Right? So this periodic movement of chest is what needs to be detected. This periodic movement in the chest is used to extract human vital sign. A vital sign means whether the person is dead, whether he's alive, if he's buried, at what distance. Let's say, for example, in an earthquake, a lot of walls and other things will fall on a person. Right? So, what is the depth at which the person is buried, and so on. So, a lot of things can be extracted. The signal transmitted towards the human target and the reflected wave from a moving surface undergoes a phase shift proportional to the movement. Right? If the target is at a different position, right, you will get a different phase shift. The detection of vital signs of human subject is based on Doppler effect. Right? All of us have studied this Doppler effect in our undergraduate or even class 12. If the object is moving at net zero displacement, then the reflected signal from the object is phase modulated. Right? Zero displacement means the object is not moving, in which case the reflected signal will be modulated in phase. If the movement is small as compared to the wavelength, the output signal at low frequency is directly proportional to the movement. Right? So the movement may be very small, right, and the wavelength may be large. So if the movement of the object or the subject is small as compared to the wavelength, the output signal at low frequency will be proportional to the movement. And higher frequencies allow signal detection with very minute variation. Obviously, because at higher frequencies, the wavelength is very small, and as a result, you can detect even a very small variation in the object. The variation could be, it could be moving laterally, it could be moving radially from the antenna, right, and so on. So these are some of the, this is some of the mathematics behind the radar operation. So this represents the S incident as a function of time t. So this is your incident wave, this is your reflected wave, right? And then you can calculate the chest movement and so on. Right? So I will not go into details of this because all of you are from varied background. So what are the issues in the detection? The first issue is clutter, right? So there may be a lot of signals that are coming in, right? So how do you know that this signal is from the due to the vital signs? Then there is a lot of phase noise. Right? As you would understand, if a person is buried inside some debris, right? So there may be reflections from various parts. It is not that you are getting reflections only from the heart, right? There may be reflections from various parts. So this needs to be detected. Then what is the frequency of operation that I should choose? Right? Because as we have seen in the previous slide, the movement is very small, 1 millimeter movement for during the heartbeat, and for respiration it is 5 millimeter. So what is the frequency that one should choose? Then what happens with the higher order harmonics? Right? You could have harmonics as well. Right? Then what is the DC offset? And then you have to do a proper signal processing. Because the antenna will only receive the signal, right? The signal has to be processed. There has to be a lot of signal processing on the reflected signal that goes on, so that you can detect the vital signs correctly. So applications, some of the applications have been listed here. Continuous patient monitoring in hospitals. Then we have non-invasive health tracking, handheld fixed devices. Right? So for example, if you want to detect heart rate, right? So this is non-invasive, or if you want to detect some other movements or some other things in the body, right? One has to have non-invasive health tracking of the body movements. Right? Then early detection of people under debris due to building collapse in a scenario of natural calamities. So this will help us save a lot of lives, right? If you could detect early, because if the person is under the debris for a long time, he may as well die, right? So early detection is important. Then human search and rescue operations in remote location. Right? Remote location where we have, some, let's say there are some people who has vanished in some remote location. Right? Or if you want to detect a terrorist hiding somewhere, right? One can apply this technology. And then there is, as one can understand, there will be a lot of military applications as well. So first, let us understand RCS calculations of human subject, because we are trying to detect vital signs in a human. So let us understand the radar cross-section calculations of human subject, let's say in X band. So X band is an example. One can do it in other bands as well. As we all know there are different frequency bands, especially in the microwave region. You have L band from 1 to 2 gigahertz. You have S band from 2 to 4 gigahertz. Then C band from 4 to 8 gigahertz. And X band is from 8 to 12 gigahertz, roughly. So radar cross section. Yes, is there anything? Okay. So radar cross section is the basic parameter of the target, which tells information about the ability of the target to reflect the incident power towards the receiver. So as the definition suggests, it is the ability of the target. So we may have targets made up of different materials. Let's say we have a target which is completely metal, right? So it will reflect completely. If it is a dielectric target, right? So it will reflect partially. So it is the ability of this target, right, to reflect the incident power towards the receiver, and that is classified as radar cross section. So we all know this Friis transmission equation. So in this, the received power is given by this formula, where your PT is the transmitted power, G is the gain of the antennas, lambda is the wavelength at the operating frequency, sigma is your radar cross section, right? And capital R is the distance between the target and the antenna. So the RCS, the sigma RCS, is defined as limit R tending to infinity, that is distance between the target and the antenna, 4 pi R square times power density scattered in the field divided by power density of the incident wave. Okay. And this is taken, this power density of the incident wave, right? So this is averaged over complete 3D space. So we have this 4 pi R square term here. So basically it is power density in the scattered field by power density in the incident wave averaged over 4 pi R, the entire 3D space. So the radar cross section area of the target is not a constant, and it depends on various factors. It depends on physical size and exterior features of the target. So exterior features means if there are any bends, like if there are any corners, right, or the surface is smooth. So a sphere will have a different radar cross section than, let's say, a triangular reflector. Right? It will have a different cross section than, let's say, a cuboid or a cube, and so on. The next factor that decides the radar cross section is the alignment of the transmitter. Right? At what angle? I'll just pause this slideshow. I'll turn on my video, right? Because some of the things. Give me a moment. I'll turn on the video as well. Yeah. So the alignment of the transmitter is also important, because you may have a, let's say, a cuboid, right? And the transmitter may be at different angles. Let's say the face of the cuboid is facing the transmitter. Right? You may get a different reading. Right? Some corner of the cuboid may be facing the transmitter. You may get a different reading. So alignment of the transmitter is also very important. Then what is important is frequency of operation. This has a strong dependence on the frequency of operation and the material that is used. So as I mentioned, you may have a metallic object, or you may have a dielectric object. You may have a lossy object, you may have a lossless object, and so on. So depending on the material that is used to construct the target, right, the radar cross section will vary. And in the different courses, we teach about the radar cross section of standard geometry, like a sphere, you have a cylinder, you have a cuboid, if you have a pyramid, what are the radar cross sections that is being taught. Then RCS of standard targets. So this is a table showing standard targets. So a sphere, RCS is 4 pi R squared. Cylinder, it is 4 pi R, small r. So small r indicating the radius, h squared by lambda. And then we have a flat metal plate. So flat metal plate, 4 pi W squared, h squared by lambda squared. And we have a dihedral corner. So the radar cross section is based on this. So sphere is used as a standard reference for RCS measurements, as its RCS is independent of frequency. So this 4 pi r squared, okay, is independent of frequency. Therefore, the RCS of a sphere is used as a standard reference. Right? Like for example, when we talk about antennas, right, when we measure the gain of the antenna, we measure the gain in reference to something. Right? So we could measure the gain with reference to a isotropic antenna, in which case the gain is given in dBIs. You can measure it in terms of dipole and standard dipole antenna, or so on. So for this RCS measurement, the RCS of a sphere is taken as the reference because it is independent of frequency. So RCS measurement of human body in X band. So RCS is a function of frequency and aspect angle. The reflection is to be strongest when the person is facing the receiving antenna. And RCS of a body is to be measured using following procedures. So this is the procedure that is given to measure the RCS of a human body. First, we take an empty room for clutter subtraction, then a metallic plate for calibration. Then, so basically, you first measure the RCS, right? So we remove all the clutter in the room. So we have an empty room. Right? And more importantly, we can take an anechoic chamber where there is nothing, there are no reflections. Then we take a metal plate for calibration, right? Metal, because the reflections from a metal are well known. Then we take a metallic cylinder for calibration, and then we take finally person who is standing still. Right? So these are the steps that are followed to measure the RCS of a human body. Because when we detect vital signs, it is important to have information on the radar cross section of the human body. So this is the measurement setup that was used. Right. So what we see here is this blue colored pyramid that you see. These are electromagnetic absorbers. So these measurements are done inside an anechoic chamber, right, where we have a lot of absorbers on the wall. There are a lot of absorbers on the wall. We have two antennas in the X band. So all of you have seen these pyramidal horn antennas. So this is one of them is a transmitting antenna. The other one is a receiving antenna. Right? And then we take a metal plate. What is shown here is we measure it for a metal plate, and then the same metal plate is bent in the form of a cylinder, right? And we take RCS measurement of that, and then finally we take measurements from a human body, which is at rest. So RCS measurements of a human body in X band. So this is a result that was obtained. So the black curve indicates front side and the red curve indicates the back side. And this is taken versus frequency. Right. So as you can see here, the data is quite random. You don't get constant RCS with frequency. So the front side, it is slightly constant. As you can see, there is less variation in the front side. Back side, there is a lot of variation because a slight movement in the body part, it will cause RCS to change, because RCS depends on the shape of the object as well. So these are some of the first results that we obtained for RCS measurements on a human body in the X band. So you can see this range from X-axis range from 8 gigahertz to 12 gigahertz. Then another thing that is used is direct down conversion demodulation architecture. So what we have here is the block diagram of the measurement system. Right? So what we see here is a respiration signal at 0.35 hertz. Then we have heart signal at 1.2 gigahertz. There's a noise source. Then these are given to phase modulator RF input. So there's an information signal block. Right? So this is connected to RF signal. Right? Then we have LOS link at 1 meter. So this is where your antenna will be. This is the receiver part. We will have LNA. We will have mixer, low pass filter, amplifier, and then you get the information signal. So, and in this part, this RF signal is divided, right? It is given to the mixer as well as it is given to this block here. So we have a power divider here, RF signal at 10 gigahertz. So what we see here is, this is the spectrum that is shown. So the frequency range on x-axis is very small. The maximum frequency is 2.5 hertz. So what we see is in the spectrum. So this is after down convergent demodulation, everything. So what we see in the spectrum is we get a peak at 0.35 hertz, right? And this is not a very strong signal. Right? This is signal processed, so this is not a very strong signal. This is minus 71 dBm, and we get another peak at 1.2 hertz, which is slightly lower, minus 89.23 dBm. So this block diagram is the diagram that will be practically used to detect the vital signs of a human body, the respiration rate as well as the heart rate. Then this is another type of demodulation architecture. So this is called as a quadrature demodulation architecture. Again, it's similar, but with slight changes. There are a couple of more power dividers here. Right? So in the earlier figure, you saw that there's only one power divider. Right? And here we see that there are a couple of more. So this is quadrature demodulation architecture. So this is a standard thing that is used in the industry. So with this quadrature demodulation architecture, again, let us compare the frequencies. Earlier it was 0.35 hertz and 1.2 hertz. Again, it is 0.35 hertz and 1.2 hertz. Okay. The signal levels are in the double down convergent demodulation scheme. The signal levels are, the signal levels were at minus 71 and minus 89. Here they are further down at minus 74 and minus 96. The frequencies remain the same. Then here it is a slightly different way of double down convergent demodulation. So we use two mixers here. There are two RF sources at 9.99 gigahertz and other is at 10 megahertz. So there are two mixers used. So in this case, what we see is you can detect the same frequencies, 0.35 hertz and 1.2 hertz, with much better signal levels, minus 25.87 dBm and minus 44 dBm. Right? So is this going fine? Just let me check. Am I audible enough and are the slides visible? Can somebody please confirm?
Yes, sir. Your slides are visible and you are quite audible also.
Okay. Now in this case, right, in the three schemes that were shown, the respiration signal and the heart signal, right, they were given as inputs, right? So these were the signals that were given as input, and you could detect them. So this is basically to show that the signals that are given at 1.2 hertz and 0.35 hertz we are able to detect through this demodulation architectures, various demodulation architectures at various signal levels. So conclusion, so we have estimated the RCS of a human subject in X-band, and different architectures to detect vital signs of a human subject using Doppler are studied. And so basically the three things, direct down conversion, quadrature demodulation, and double down conversion, they were seen to see if the signals that we are getting are, we are able to detect or not. It is not only detection and then doing signal processing to get the signals right. So as you can see here, the signals are properly detected. The noise floor is much lower. So now we see next is VNA-based vital sign detection. So we'll go to the measurement setup at 2.5 gigahertz and 10 gigahertz. The measurement setup is as shown here. So we use a vector network analyzer. So this is a 50 gigahertz vector network analyzer. This is 2.5 gigahertz setup. So we have a transmitting antenna and we have a receiving antenna. So you can see the size of the antenna is much bigger here than a 10 gigahertz antenna, which is X-band, which is a small size. Right? So these are connected as a transmitting antenna and receiving antenna to a vector network analyzer. Right. So just a few things here. The VNA is used at 2.45 gigahertz and 10 gigahertz with a sweep time of 10 seconds. The sample points collected are 16K. There are three kinds of measurements taken for respiration to resemble the real life situation. First is normal breathing, right? You could have different rates of breathing. So normal breathing, fast breathing, and very fast breathing. Right? So under these three conditions, the measurements are taken. Background measurements are also taken in the absence of human subject, keeping the whole setup same so that we can remove the noise. Then for all measurements, the distance between the measurement setup and the human subject is 500 centimeters, that is 0.5 meters. Sorry, 50 centimeters, that is 0.5 meter. The reflected RF wave from the human subject carries information in the form of S21 magnitude and phase. So this S21 is a scattering parameter, right? So this is basically the transmission parameter. So when you give input to one antenna, what is received after reflection at the second antenna is what is S21 here. So we get the scattering parameter S21 is a complex parameter. It has information on magnitude of the reflected signal as well as its phase. The phase of S21 contains variation of chest movement and can be used to extract the vital sign information. So one of these antennas is used for transmitting, other is receiving. Right? So in the received signal, we have the amplitude as well as phase. So the amplitude part is used to extract information on what type of target it is, and the phase part, as is said here, the phase of this signal, reflected signal, it contains variation of chest movement and can be used to extract the vital signs of the information. So basically, both magnitude and phase are used to detect the heartbeat, the chest movement, basically, right? So chest movement is because of two things. One is your respiration, and second is because of the heartbeat. So both these things we should be able to detect. So this is the measurement setup, and this is phase of S21 in degrees versus time in seconds. Okay, so this is for normal breathing at and the signal is at 2.45 gigahertz. So there are two curves here. First is from the human body, this black curve. So as you can see, with time, the phase varies, and the red is from the background. So from the background, there is no phase variation. Okay. Similarly, this is again shown. So this is basically normalized thing. The phase of S21 in degrees normalized, or the same graph but normalized. So the reference, background reference is at 0 degrees here. It's 0 degree phase. But with reference to that, we are now plotting the phase of the reflected signal from the human body. Now, so this was for normal breathing, right? So then we have fast breathing. So you can see in the fast breathing, right, there are multiple curves here, multiple ups and downs here, because we are now the object or the target is breathing fast. Right? So if it is again at 2.4 gigahertz. Now in very fast breathing, again you will see. So just compare the three graphs. So this is normal breathing. So you'll see less variations here. In the fast breathing, the variations have increased. And in the very fast breathing, the variations have further increased. Right? So in the phase, you can see that you can detect whether it is normal breathing or fast breathing or very fast breathing. Right? So in the phase, we have that information. The task is to extract that information and find out the corresponding frequency. So signal processing is done on that, and what we get is spectrum of the respiration signal. Right? So there are three curves here. So we have normalized spectrum on the y-axis, and we have frequency on x-axis. So what we see is there are three curves, black, red, and green, corresponding to black corresponds to normal breathing, red corresponds to fast breathing, and the green corresponds to very fast breathing. Okay. So as one can expect, as the breathing rate increases, right, the heart movement, the frequency of heart movement will increase. So for normal breathing, we have 0.4 hertz. For fast breathing, we have 0.6 hertz. And for very fast breathing, we get 1.01 hertz. Right? So because when we detect, the object may be breathing at different rates, right? So it could be normal breathing. So one can understand if the object is at a normal position. If it is fast breathing or very fast breathing, so there may be some problem and so on. So we should be able to detect these three cases separately. Right? One can also do for very slow breathing as well, right? But that is not shown here, but one can do for very slow breathing as well, because at times your breathing rate may decrease drastically, right, under certain conditions. So that also one should be able to detect. Now, this was at 2.45 gigahertz. Right? The same thing is done at 10 gigahertz. So this is for phase of S21 for normal breathing. Right? Then we have, so these two graphs, one is the phase that is detected, and the second one is normalized. So we take this background noise as the reference, and then we normalize it with respect to the background phase. This is fast breathing. Again, as you can see, there are more variations here. And then this is very fast breathing. Still more variations. And the spectrum shows the following things. So we have, for normal breathing, we have 0.404 hertz. Fast breathing, we have 0.7 hertz. And very fast breathing, we have 1.11 hertz. So we can, I just go back a few slides. So this is 0.4, 0.6, and 1.01. Here it is 0.4, 0.7, and 1.11 hertz. So there's slight difference at two frequencies, right? Because the RCS of the body depends on frequency, is frequency dependent. So at two different frequencies, there's slight change in the respiration signal that we get. Right? Now this is through the wall. So these measurements were done when the object was directly standing in front of the radar system or the antenna. Now, what happens when we do through wall measurement? Let's say the object is standing at one place, then there is concrete wall in between, and the antennas are on the other side of the wall. So this is called the through wall measurement. So this graph here shows phase versus time. Right? As you can see now, the signal has weakened. Right? The phase variations are not very large, like in this case. Right? There is large phase variation. Right? Top to bottom, there is large phase variation. When we have wall in between, right, the variations are not very high. Right? The variations are small. Now, this is phase of the reflected signal from human body. So same thing with this phase of the reflected signal from the background subtracted. And if we take the spectrum of that, what we see is, so we have normalized spectrum versus frequency. So respiration rate at 0.5 hertz. Okay, so this is through the wall. Please remember, this is through the wall. Then we have second harmonic coming up here. Then there is heartbeat at 1.3 hertz and so on. So the heartbeat signal is very weak. As you may have, as I told in the initial this thing, the heart movement, the chest movement due to heartbeat is very small. As a result, what we see is a weak signal for the heartbeat. However, the frequency is more or less same, 0.5 hertz and 1.3 hertz here. So this was at 2.45 gigahertz. Then we do at 10 gigahertz. So again, similar graphs. The spectrum here shows 0.5 hertz for the respiration rate, and we have second harmonic here. Right? The heartbeat is very weak here. The movement due to heartbeat is very weak, right? And it is almost close to the noise floor. So from these graphs, one can see that the lower frequency of 2.45 gigahertz is slightly better for this detection, vital sign detection. So conclusions, using VNA, the respiration rate of human subject is estimated under different breathing rates. The VNA is very bulky because when you want to take this system to the actual site, let's say there's an earthquake and a building collapses, you cannot take a VNA there. So this is VNA is bulky and it is also expensive. So this is the major disadvantage. However, you don't the VNA that is used is a very general purpose VNA, and you don't need a complete VNA. You can design a circuit which takes in your phase and phase and amplitude variations, right, and then does the signal processing. So the system can be very small as well. The VNA that is used in this study is a general purpose VNA, and it need not be used all the time. Then through the wall human subject respiration rate detection. So in this case, the through the wall measurement is to detect respiration signal using direct demodulation is demonstrated at 2.4 gigahertz. The system is tested in all kinds of real life situations, such as different breathing rates and different medium behind the human subject and so on. So you need not have the concrete wall all the time. You may have a glass in between, you may have a wooden wall in between, and so on. So there's a particular algorithm called as HVD is applied to extract the respiration signal. The transmitted power towards the human subject was 5 dBm. So these specifications are important. The information signal was required for 50 seconds. Right? The reflected signal, it was collected for 50 seconds to get better resolution. And the
Sir, your voice is not audible.
my voice is not audible.
Yes, now it is audible, sir.
Okay, maybe there's some problem. So we have this direct down convergence system. We have a transmitting antenna, right, which transmits electromagnetic waves to the human body. And the waves reflected from the human body are collected by receiving antenna. Then we have a standard receiving system. There's a mixer. There's a low pass filter. We have a data acquisition system. There's signal processing done. And then what we get is the final vital sign detection. So this is the system that is used. So human subject is at 0.5 meters from the radar. Again, this is at 2.45 gigahertz. Right? So we get respiration signal at 0.35 hertz. Right? Second harmonic is shown here. The heartbeat signal is not. So because here the interest was in the respiration signal, so more focus is on the respiration signal at 0.35 hertz. So the distance is varied. So this is at 0.5 meters from the radar, human subject. So if the human subject is taken to 2 meters from the radar, again you are able to detect the signal, respiration signal at 0.35 hertz. There's second harmonic here, right? And there's also a small sort of signal in the lower case, but we have seen that this is not significant. You can detect the respiration signal quite nicely. Right? Spectrum is almost touching 1 here. So at 0.35 hertz, even at 2 meter distance from the radar, one can detect the respiration signal. And further 3 meters, right? As you can see here, the signal that is shown here is not very good. Right? In the earlier cases, say for example 0.5 meter, the baseband signal in millivolts is good signal. But at 3 meters, the signal becomes very noisy. Right? As a result, your second harmonic has increased, right? And the respiration signal is still at 0.35 hertz with very good spectrum. Right? So this is done, these three measurements, 0.5 meters, then 2 meters, and 3 meters. These are done when there is nothing between the radar and the human subject. The next case is where the subject stands on one side of the wall and the antenna is on the other side. Right? So you can see this is 15 centimeter wall, concrete wall in between. Right? The radar is on the one side of the wall and the human subject is on the other side of the wall. So this is the measurement system. So this is in one room. Right? Then there is wall here, and on the other side of the wall, there is a student standing there. Right? So to detect the signals. Right? So the block diagram that is shown here is all, the equipment is all shown here. So you have data acquisition system, you have signal processing system, and so on. And these are the two antennas, horn antenna, transmitter antenna, and the receiver antenna. So this is a small bit on the HVD algorithm, Hilbert vibrational decomposition algorithm. So again, I will not go into details of this. So this is basically to the signal processing part here, right? This block signal processing part here. After the data is acquired, right, then we have signal processing. So the signal processing is done through this Hilbert vibrational decomposition algorithm. So this algorithm is well known for different estimation, detections and estimations. However, we have used this for the first time for human vital sign detection. So when we have wall in between, what we see is in slow breathing case, right? So this is your baseband signal. So the red one shows no human subject. So this is basically your noise flow. And when the human subject is present, this is the baseband signal that is seen here. Right? The spectrum, right? So this is fast Fourier transform without HVD, that is Hilbert transform, and red one is with the HVD. So what we see here is with HVD, FFT with HVD, when we take the FFT of the baseband signal to get the normalized spectrum. So what we see here is we get respiration rate at 0.14 hertz, right? And the spectrum is clean spectrum. Right? Similarly, this is power per frequency, dB per hertz for with HVD and without HVD. So we can see that with HVD, the red curve here, right, in this graph is very smooth. So this HVD algorithm works very well for our purpose of human vital sign detection. Then this is normal breathing. Again, in normal breathing, so this was slow breathing. So this is 0.14 hertz. Normal breathing, the signal is respiration rate signal is detected at 0.28 hertz. And then we have fast breathing, slightly more. So the detection, so you can see the difference here. FFT without HVD, it has other components as well. Whereas FFT with HVD, right, you get only this component, right, 0.74 hertz. So this is the respiration rate that is detected for fast breathing. Then what happens when we have low transmitted power? Because the power that is used, right, for transmission, it is also very important. So when we have low transmitted power, so this is under normal breathing condition. Again, you can detect the signal very nicely. So this is at 0.26 hertz. So this is about the detection using wall. Right? So you have radar on one side of the wall and human subject on the other side. So what is shown in these graphs is you can still detect, even if there is a wall, you can still detect the respiration rate, right, for under various breathing conditions, slow breathing, normal breathing, fast breathing, right, and so on. Then at low transmitted power, because you have to choose the power that you transmit, right? So even if you have low transmitted power under normal breathing, this is shown. So this was also done for fast breathing, very fast breathing, and so on. But what is presented here is only for normal breathing. So you can, what is seen is you can still detect the respiration rate even at low transmitted powers. So I will request the organizers to tell me when to take a break. Right? So now next part is when human subject makes an angle with the radar. Right? In this case, the radar, right, this transmitting receiving antennas and the human subjects, they were in line, right? They were in line. So what happens if the object or the human subject is at a different angle? It is slightly moved, right? So that from the antenna it makes certain angle. Instead of 0 degrees, it is at certain angle from the radar. Radar essentially would mean the transmitting and the receiving antennas. So this is the experimental arrangement. So we have brick wall here, and the human subject, right, is rotated. Instead of changing the angle from the antenna, the human subject is rotated. So at first, the human face is facing the radar, then we rotate, then we rotate, then we rotate, so that your back faces the radar now, and so on. So what we see here, the table shows angle of rotation. So this is the axis of rotation that is shown here. Right? The human subject rotates around its own axis. So at various angles, what are the frequencies, what are the signals detected, and what are their frequencies for normal breathing as well as fast breathing. So as you can see, at various angles, the variation is not much. Right? So the minimum that we have is 0.22 hertz, and maximum that we have is 0.30 hertz. Right? So this is at 45 degrees and 270 degrees. Now there is no specific variation. So this is for normal breathing. For fast breathing, 0.74 to 1.05 is the variation. So we can detect this as well quite accurately. So this is the variation is not very large, 0.74 to 1.05 hertz. So moreover, the point to note here is also that at different angles, there is no definite trend that is followed here. Right? Like you can see here, the normal breathing, the frequency has decreased, then increased, then decreased, then increased. Right? So there is no specific trend, whether it is going down all the time or it is going up all the time. So there is no specific trend, and the errors that are random errors, right? So if you repeat the experiment one more time, you will get similar frequencies for various angles. Now, what happens when the human subject background changes? Right? The person may be standing in free space with nothing behind him, right? Like air behind him. The frequency is detected as 0.24 and 0.74. If there is metal plate kept behind the person, right? So we are trying to basically simulate and practically do different scenarios. Right? The person may be in free space. The person may have a metal on the backside. Right? So again, we're trying to detect the respiration rate. So with wood, if he has a wooden, let's say wooden plank on the backside, right, what is the frequency that is detected? So through all these experiments, right, this vast set of experiments. So through all these experiments, what we see is you can detect the respiration rate under various breathing conditions, normal breathing, fast breathing, and so on, quite accurately, right, with this radar system and with the signal processing algorithm, Hilbert vibrational decomposition algorithm that was used. So we can detect the respiration rate quite easily. So the respiration rate, again, I would repeat, is detected through the movement of the chest. Right? So there is chest movement due to respiration, there is chest movement due to breathing, due to heartbeat, sorry. So under different conditions, we are able to detect the vital signs. So basically, you will be able to tell whether the person is, breathing normally or he is fast breathing. So depending on that, you can estimate what kind of danger he is in. Right? Plus various backgrounds. Right? In the actual scenarios, the person may have different backgrounds. He may not be always in free space, right? Because he's buried inside the debris. Right? So there will be something on the backside as well. So what happens if we have different backgrounds? So again, we see that the respiration rate is properly detected. So you can detect the signal quite accurately. Then second study is when the human subject is 1 meter from the initial position. In this case as well, you can detect the respiration rate. So we're trying to basically try and give various, real life scenarios so that we should be able to detect the respiration rate accurately under various conditions. So this is when the human subject is 1 meter from the initial position. This is when it is 2 meter from the initial position. Right? Again, you can see that this peak at 0.2 hertz remains unchanged. And the two curves here indicate the, it indicates that this HVD algorithm, right, is better than without HVD. So if we take fast Fourier transform without HVD, and if we take fast Fourier transform with HVD we get a clear signal. Now, through the wall measurement of respiration of multiple human subjects. So it may not be, it is not necessary that there is only one human subject present. We could have multiple human subjects. So again, there is a wall inside and there are multiple of subjects here. So there is subject 1, there is subject 2, and then there is radar on the other side. So what happens if we have multiple subjects? Can we detect the multiple subjects accurately is what was seen. So what is seen here is human subjects are breathing at different rates. Okay. So both subjects may be slow breathing, one may be normal breathing, other may be fast breathing, and so on. So in the first case, the first scenario is slow breathing and normal breathing. So what we see in subject 1 is slow breathing. We could detect its signal at 0.1 hertz. Subject 2 is fast breathing, normal breathing. We could detect its signal at 0.22 hertz. Then second scenario is slow breathing and fast breathing. So we could detect signals at 0.16 hertz and 0.46 gigahertz. Then we have both subjects normally breathing. Right? And please remember, this is through the wall. Right? The subjects are on the other side of the wall. Again, we could detect. So normal breathing for different persons will be different. So one subject was 0.33 hertz, the other subject was 0.22 hertz. Then we have normal breathing and fast breathing, and both fast breathing. Again, this the value that we see here, let's say for both fast breathing, 0.64 hertz and 0.4 hertz, they need not be same because different people will breathe at different rates, right? The frequencies will be different. So, but we could accurately detect that there are two separate subjects, right, breathing at different rates, 0.64 and 0.4 hertz. Then 3 human subjects breathing at different rates. So these are the graphs. So this is the normalized spectrum without the transform, HVD transform. Then we have subject 1, baseband signal, subject 2, subject 3, and so on. So we could detect subject 1, subject 2, and subject 3 separately at 0.14 hertz, 0.2 hertz, and 0.4 hertz. So they were at different positions and breathing at different rates. But in the real life scenario, you may have different persons breathing at different rates, and their orientation may be different. They may be at different positions, they may be at different distance from the wall, and so on. So we are trying to incorporate all those scenarios, and we could see that we can detect the signals quite nicely. So again, there's a different algorithm used. Through the wall respiration rate detection of human subjects using sparse decomposition. So the respiration signal of human subject is extracted from the noisy signal by using multiple scale structures using self-consistent nonlinear waves sparse decomposition, SNSD. The algorithm is applied on received signals and checked whether we can extract any useful information, and the measurements were done at 2.4 gigahertz. So this is the theory of signal decomposition. So I will not go into details of this. So these are simulated signals. So signals were simulated at different frequencies. Then simulated in the simulated results without the decomposition, sparse decomposition algorithm and with decomposition algorithm. So we can detect two signals, 0.25 and 1.2 hertz. Okay. This is the PSD of two different signals. So in the measurement setup, again, we had the distance was 0.4 meters from the wall. Subject was at 0.4 meters distance. The radar was also at 0.4 meters distance. So on one side of the wall and on the other side of the wall, we have this setup. So again, here we could detect, this is using a different algorithm. The earlier results that we presented, so these were using Hilbert transform. Now we have sparse decomposition method. So second algorithm that is used to detect signals. So again, with this as well, we could detect signals quite clearly, 0.25 hertz and 1.2 hertz. So actual human detection. So you could detect at 0.24 hertz, quite a good signal. So this is THW, so through the wall signals. So in the conclusion, human subject respiration rate is estimated in complex environments, trying to simulate various real life scenarios. Respiration rates of multiple subjects are estimated. The algorithm can detect the information signal and even in noisy environment, and processing time and complexity are quite less in this case. But as I mentioned, the measurements are all done using a vector network analyzer. The same thing can be done using, by coming up with a dedicated circuitry, right, which includes data acquisition as well as the signal processing part on a single board. So in that case, the detection, the overall system will be quite handy. Now, subject localization. Okay, so we have detected that there is a subject. Now, how do we locate its position? Okay, at what distance it is? So in this case, localization of the target is done by finding the range, at what distance it is, and the angular position from the antenna. So if there's an antenna here, whether the subject is here or here or here, right, and at what distance it is located. So range is detected by transmitting two frequencies simultaneously and detecting the phase difference of the reflected signal from the target of these frequencies. The range is directly proportional to the phase difference and inversely proportional to the frequency difference. These are standard things that are used in radar. The direction of arrival, DOA, is estimated by multiple signal classification algorithm, which is standard music algorithm. So for M, if we have M sensors, you can detect M-1 direction of arrivals. For different medium between the radar and human subject, the direction of arrival is estimated. Then we use a antenna of 4 patches to receive the reflected signal from the human subject. The patch are in this array are separated by half wave. So these are some details of the system. So we have a subject here, which is at 0.75 meters now from the wall, and the radar is at a distance of 0.5 meters. So this is dual frequency Doppler radar for range and respiration rate detection. So earlier it was at one frequency, either 2.4 or 10 gigahertz. Now we have two dual frequency Doppler radar. So some theory on the dual frequency radar operation is given here. So direction of arrival estimation using arrays. As I mentioned, there are 4 arrays. So based on the phases of the signals that have arrived, we can detect the direction of arrival. So the actual measurement setup is as shown here. There is a there's an array of receiving array here. There is a transmitter, single transmitter, and 4 antennas in the receiving array. So each of these will have its own system. So channel 1 from each receiving antenna, we have 1 channel. So there are 4 channels, and the subject is on the other side. You can estimate the angle of arrival as well. So this is normal direction, then positive thetas and negative thetas. So this is the, you can see all these 4 channels here, data acquisition and signal processing and all done in the lab, our lab here. So these are transmitting and receiving antenna. And so this is transmitting and receiving antenna, and you have the array of patch antennas here used in the receiver. So more close-up view of the setup. So this horn antenna is used as a transmitter, and then we have 4-element array, linear array of 4 elements of patch antennas here. So the subject is standing here. Right? So what we have is, so we have a wall here, right? Then at some distance from the wall, there is a wooden sheet, and then the subject is standing. Right? So you could either have a wooden sheet, or you can have a glass in between. Instead of wooden sheet here, what is kept here is a glass sheet. Right? So various scenarios were studied. And what we see here is normalized spectrum again. So this is black one is after correlation. Red one shows the FFT of received signal, and green curve shows FFT after the Hilbert transform HVD algorithm. So we can detect the signal quite accurately at 0.22 hertz. So this is for the spectrum function for various angles. So you can detect at like this black curve is for -22 degrees, red curve is for +24 degrees, and this is your normal direction 0 degrees, green curve. So normal breathing and medium is air. Now the second is medium is glass and wood. If the object is behind a glass and wood, so you can see here this thing, the respiration rate, respiration signal is detected at 0.18 hertz, and spectrum function indicates the estimated direction of arrival. So estimated direction of arrival is 0 degree here. So both things can be detected. So this is a table showing through the wall different medium between radar and the human subject. So first is when there is air, different breathing conditions, slow breathing, normal breathing, the actual distance and the estimated distance. So slow breathing for different mediums, it ranges from 0.12 for air, 0.08 for wood, glass it is 0.12, and wood and glass combination it is 0.1. So you can detect the signal under slow breathing condition as well as under normal breathing conditions. And the actual distance is 1.4 meter between the radar and the human subject. The estimated distance is 1.68, 1.85, and so on. So this is a good estimate. So you can see that there's a difference of 0.2 to 0.4 meters between the actual distance and the estimated distance. Now this can be improved upon. So there is a scope for research here. So at this point, I would like to mention that there is a scope for improvement because the actual distance is 1.4. What we detected was 1.6 or 1.8 meters. So there is a slight variation here. One can improve this estimation as well with a slightly better system. However, the breathing rates were more or less similar under different conditions. So signal to noise variation for the reflected signal from the human subject with distance. So as the distance increased, what we see here is the signal to noise ratio decreased. Obviously, it's expected. Then the actual error in theta, delta error, when the signal under different signal to noise ratio conditions. So as one would expect, if we have higher signal to noise ratio, higher SNR, the error will be less. If the SNR is low, the error will be more. Right? So if you use better signal to noise ratio, your estimation, the distance estimation here will be better. Now, same thing for RX arrays, reflected receiver arrays and one transmitting antenna. And there are two subjects now. Right? So the two subjects are at different positions. Right? So this is at 0.5 meters from the normal, and this is at 0.8 meters from the normal. So the distance between the two positions is 1.3 meters. So again, estimated direction of arrival is minus 34, 40. So different conditions were seen. So minus 34 degrees, 47 degrees, minus 19, 14.5, minus 29, 24 degrees. So direction of arrival estimated from different locations. And there are two subjects now. There's one subject or one human being standing at this position. The second human being is at this position. So what is checked here is what happens if I change their positions. Right? So we were able to estimate the direction of arrival even if the positions change. And this is also very vital when we try to locate bodies under debris. So the conclusion is human subject range and direction of arrival are estimated. For different medium between the radar subject and the DOA, range and respiration rates are estimated using this proposed methodology. So what we see in all these experiments is even if you have different, different things, different material between the radar and the object or the human being, okay? The human being could be at different angle between the angle with respect to the radar system. You can still detect the vital signs. You can still detect the respiration rate using the proposed methods. So are there any doubts till now? I'd like to take some questions based on this before we go on to the loss modeling part.
Now participants can ask the questions if anybody has any questions, or else you can put the chat box also.
Chat box questions probably I will be able to answer at the end, because when I'm doing the PowerPoint presentation, I won't have access to the chat box. So if there are any questions, couple of questions, I will be happy to answer.
So there is one question in chat box, sir. Can I read it?
Okay. So
why ultra wideband MIMO technology is used for through the wall respiration identification? Have you used ultra wideband pulse for your study? Using ultra wideband signal for 3 meter or more distance between human and VNA might provide better resolution. Question from Jeet Banerjee.
Yeah. So hello Jeet. So we haven't really used UWB MIMO for through wall respiration identification, but we have used UWB for some other purpose. So what we have seen is in UWB, where you do a pulse transmission, like UWB pulse is transmitted and reflected pulse is analyzed. Right? So that gives you better accuracy, that gives you better resolution, because the number of frequencies that you are looking at, right? So each frequency component will have certain information. So the number of frequency components that you're looking at is large. So as a result, you definitely get better resolution using UWB technology. However, the problem with one of the problem with UWB technology is you have very less power to transmit, right? Because it is spread over the entire spectrum, entire UWB band. Right? The power that is used in UWB is much lesser. So although you may get better resolution, identification at times may be a problem, right? When you have complex real life situations. Right? So we have not done this studies with UWB antennas, but we have used UWB antennas for some other purpose. So there a complete UWB system was developed to to work as a radar. Right? So this was basically used for image processing algorithms, not for human vital sign detection.
Sir, am I audible?
Yeah, yes, G.
Yes, sir. Thank you for the presentation. It was very informative and very well presented.
I'm still to complete. I have some part left.
Yeah. Just I had one question, sir. I have seen your experimental setup, and there I have
Yeah.
seen there is one horn antenna which is being used as transmitter, and you are using four elements in an array as the receiving
Right.
antenna, right?
Right.
So
Right.
instead of using an antenna array, if we use multiple input, multiple output antennas, will it be suitable or valid?
Arrays concept is slightly different than multiple input, multiple output
Yeah.
antennas.
Yeah.
As in case of arrays, what we are trying to do is we are trying to use arrays for DOA estimation, right, wherein the phase or at each of the receiver is monitored, and then it gives you the basically direction of arrival. In MIMO antennas, what we are doing is you're feeding the antennas separately. Right? It is each antenna is in fact a separate system. It does not improve the overall gain or so. Right? So MIMOs is a completely different concept than your arrays. Also, although there are multiple antennas used in both the cases, but that is a completely different concept. And I don't believe that using a MIMO, right, for instead of an array here will serve any purpose. That will not serve any purpose. Arrays is complete. So direction of arrival, it is arrays. What you can have is you can have MIMO configuration and array of that MIMO configuration.
Okay.
You can have MIMO configuration and array of that MIMO configuration. That is possible. But only MIMO, let's say 4 antennas, 2x2 MIMO that used for this will probably not serve any purpose as far as direction of arrival estimation.
One last query from my end. That is why I asked this question is when we go for MIMO, we find that using multiple antennas reduces the bit error rate. It means reliability of communication will increase. So if we are not getting a good resolution, if suppose due to some kind of things there is large bit error rate, so this we can get reliable data from this through the wall sensing. Therefore, I have asked this question.
Yeah. So that's what I said. You can use MIMOs, right? MIMO, treat that as a single element, and then you can copy that in an array. Right? So that will give you better resolution, and you can also use UWB antennas in the MIMO. But you declare an array so that you get you correct an estimation of the direction of arrival.
Thank you very much.
Any other questions?
This sir question has answered by sir. Have any other questions from the other participant? Any other participant has any question?
Okay, then I might continue.
Okay.
And we will break around close to 1 o'clock for lunch break, and then I'll continue after the lunch. Is that fine with the organizers?
Yes, sir. If participants don't have any problem. Hope participants are okay with that part. Can anyone give me? Yes, sir. We can go ahead.
Yeah.
Up to 1 o'clock we will continue. Then we can go for a break.
Yeah. Okay.
Right. Thank you.
So the next part of the presentation will deal on about the loss modeling for different material in S-band for vital sign detection of the human subjects. This is very important, loss modeling, because important, but at the same time it is not very difficult to do this loss modeling, because as we have seen in the earlier presentation, you may have different material in between the radar and the human subject. Right? And different materials means it will have different properties, different electromagnetic properties, different losses. Right? So it is very good to have an estimate or to have a library of these properties, right? So that we know what is the material as well. So for example, we have done some standard materials. We have put a glass in between, we have put a concrete wall in between, we have put a wooden plank in between, and we have put combinations of those three things. However, in the actual scenario, you may have completely different thing in between. It may not be a concrete wall, it may not be a wood, it may not be a glass. Right? So what we have tried to do is we have tried to do a loss modeling of different materials and in a convenient band. So S-band was convenient to us, so we have tried to do it in that band. The experiments can be repeated in other bands as well. Okay. So this is the last part of the first talk here. So we have done loss modeling for different materials and different thicknesses. And this is done in S-band, 2 to 4 gigahertz. The debris may be thick and have different materials like concrete, brick, wood, glass, and so on. The thickness of the debris can also vary in real life scenarios. So we're trying to estimate under different conditions. We're trying to model the losses under different scenarios here. So first is through the material simulated and measurement results. So what we see here in the first graph on the left side is S21. S21, as I mentioned earlier, is basically transmission. Okay, so what is the transmitted power in relation to the incident power? So this is done for different thicknesses of wall. So the wall may be 5 centimeter thick, 15 centimeter thick, so on up to 45 centimeters thick. So what we see here is the transmitted signal, right, through the wall transmitted signal decreases as we increase the wall thickness. Right? So this is something that one needs to understand. Although we may know this beforehand, but it is good practice to conduct these kind of experiments. So for different wall thicknesses, the transmission is shown. So as the wall thickness increases, right? As the wall thickness increases, we are going down this line here. The transmission decreases. Right? Through the wall transmission decreases. So this particular graph on the right side shows for normal, for one particular thickness, simulated, measured, and no material. So the green one is no material, so directly received signal. Then we have measured signal, the red curve, and black curve is the simulated signal. So what we see here is the no material signal is also measured signal. So what we see here is the no material curve and the simulated curve for this thing is closely matching. So we don't have too many losses in this case. So this is for a wall. Now this is for simulation and measured result for different thicknesses of wood. Again, one would expect, as we increase the thickness of the wood, right, the losses will increase. Right? So in this case, the measured and the simulated results, they slightly vary because this is for a wood. Right? So in the simulated results, right, they show slightly more transmission. Now it is, when we say simulated results, it is very important to assign the material properties accurately. Right? And you may not know the exact properties of the wood all the time. Right? Similarly, if we take, like our experiences, if we take wood from, let's say, different trees, right? So a mango tree, a wooden sheet from mango tree will behave differently than a wooden tree from a neem tree. Although they are all dried, right? They're dried woods, but the properties may slightly vary. So in the simulated results that we see here, right, they are slightly different than the measured results. This is mainly because if we don't take into account the exact properties of the wood that is used, right? Plus, there are different types of wooden boards that you will get. So different wooden boards will also behave differently. There may be slight variations in the different wooden boards. So that is the reason there is a slight difference here in the simulated and measured results. Then this is for different thicknesses of glass. Now, surprisingly, what you see here is if we increase the thickness of the glass from 20 mm to 100 mm, right? So 100 mm is quite some distance. So 10 centimeter thick glass. The losses, right? They are not very high, right? The losses are not very high, unlike in case of this, in case of wood or in case of concrete. Right? In this case, what we see is the losses increase with thickness, and the variation is only 5 centimeter to 45 centimeter. In this case, for the wood, it is 1 centimeter to 15 centimeter, and for glass, it is 2 centimeter to 10 centimeter. So the variations here are not very large. Right? Even if I use a 20 millimeter thick glass or a 60 millimeter thick glass, so the difference is not much. Right? So this is again, depending on the type of the glass, the results, the simulated results will vary, and they will show differences with the measured results. Right? So the green curve again shows no material present, this is the measured results for different material, wood, wall and glass put together. So same graph. So same results put together in a graph. So black one is the no material. Then we have wood, glass and brick. So what is seen here is the glass is slightly lossy at lower frequencies. Right? Otherwise, at higher frequencies beyond 3 gigahertz, the transmission loss, right, is similar for all the materials. Right? And that loss is not very different than the case where we have no material. Right? So the losses are not very much. So this data is very important when we study vital sign detection through different materials. The simulated and measured results again. So we have transmitting antenna and receiving antenna, and then this is the material. This is different materials that's shown. So S21 simulated and measured, they're nearly same, except that there are like these deeps are more prominent here in case of measured ones. This is for various thicknesses. These are the various wall thicknesses. This wall, it could be of any material. So various wall materials. This was also done. Then we have a combined. This is a concrete wall, then wood, then glass, and a metal plate. So if we have a combination of these, what do we see? So now here again we are actually looking at the reflected signal. In this case as well, we were looking at the reflected signal. So that was used as S21. In this case, again, what we see here is there is not much difference between simulated and the measured results. They follow similar patterns. Right? And in this case, unfortunately, without any material, there is no data shown here. But what we see here is simulated and measured results follow similar patterns. This is with simulated and measured results for 3-layer skein model. So we have concrete wall, we have wood, we have glass, and instead of a metal plate, we now have a 3-layer skein model here. Right? So the properties of the skein were taken from literature and they were put here. So again, what we see here is simulated showed almost very slight variation with frequency. Measured ones show more frequent, like a lot of variations with frequency. Okay. So this is not very, what is seen in this experiment is the skein model that is put here, right, is not very accurately modeled because the simulated and the measured results are quite different. Unlike this case where they were, quite closely matching. So measured results for different materials. So black one is brick wall only. The red one is brick wall with metal. Of course, since we have metal, there's large reflection. As a result, we have the S21 is more here. Then we have brick wall and wood, green curve. Then blue curve is brick wall with and subject. So subject could be a human being. So what we see here is there is similar variation that is followed. So from this analysis, one can say that even with different thicknesses of the material in between the radar and the subject, one can accurately measure the vital signs. The only change is if you have a metal here. If you have metal backing, then there is slight difference here. Otherwise, in the rest of the 3 cases, it is same. So it does not matter whether it is a brick wall with wood or it is a brick wall with metal or it is a brick wall with subject. You will get similar kind of variations. So these are measured results for various things. Wall, this black curve here shows wall, wood, glass, and metal. So obviously reflections are more. So transmitted S21 will be more, and this is with subject. And this is S21 for metal, glass and metal, and glass and subject. So with for glass and subject, one would expect less transmission because less reflection. So S21 will be slightly less here. Okay. but that for metal and glass and metal, it is almost exactly matching each other. A human subject is present at a distance from the wall. The black curve shows wall and metal response, and the red curve shows 50 centimeters from wall and subject. So instead of metal, we have subject here. So S21 is measured for different cases. Obviously, wall and metal will give you more reflection, so S21 will be slightly more in that case, whereas for wall and the human subject, it will be slightly less. So I covered this very fast, I suppose. Okay, so the conclusions and some indications to the future work. So the detection of respiration signal in complex life scenarios is done, and we have seen that under different conditions, you can still get the frequency for the respiration signal. Under different breathing conditions and different medium between the radar and the human subject, the respiration rate can be detected. There were two algorithms that were used, HVD algorithm and sparse detection algorithm, sparse decomposition algorithm. Then the localization of the human subject and the debris was done. Then the architecture that was used was simple, except the VNA part, which, as I said, can be replaced. VNA is a general purpose measurement equipment. So you can replace the VNA with anything, with a specific instrumentation that is required for this. And then portable devices can be used for detection of human subject under debris or behind the wall. So future scope, and this work can be further extended in many ways, which can lead to new standards in security, disaster management, and medical care. In future, the localization of multiple humans and detection of their vital signs can be done. So right now, what we have done experimentally is 2 subjects, 3 subjects. Right? So instead of that, you can detect multiple subjects. So we'll have to expand the measurement setup as well as the algorithms, so that multiple humans, say for example, if you have a group of people and you want to detect if there is some drastic behavior in one of the human subjects, so we should be able to detect that when we have multiple humans in a group. Then through the wall imaging can be done to improve the accuracy. So along with the detection, you can as well incorporate imaging so that the subject is accurately detected. So for example, we have done this orientation study. Right? So the human subject who is under the debris may be oriented in any particular fashion. He need not be always facing the radar. He may be at an angle. So we have done those studies. But along with this detection, if we can do through wall imaging as well, it will be better for accuracy. It will improve the accuracy of the overall detection system. So that can be implemented. Now, how does imaging plus this radar thing? So in imaging, again, you have similar thing. What do you do in imaging? You have a radar, right? There's a transmitting antenna, there are receivers, right? So based on the reflected signal, you construct, so slightly different signal processing is done. You construct the image, right, of the object, right? And that we have done in UWB band as well as in I think C band. We have done that imaging part as well. So next step can be combining these two things, imaging as well as the vital sign detection using radar. So you'll get better accuracy. So you can see if there are multiple objects, right, or which are not detected in the radar, right, through respiration rates. So that can be done through imaging as well. So this can further improve the accuracy. Sometimes it may so happen that the imaging is not proper, but you are able to get the respiration signals. Right? So depending on either of these two or both, it can actually improve the accuracy to quite some extent. So thank you. So before ending, what I'll do is I'll do a quick recap of what is presented so that we don't get lost in the very quick recap of what we have seen in this talk. So initially, we looked at the radar, general principle of the radar, how does it work, and what all parameters we can extract of the target. Then RCS calculation of the human subject at X band frequencies, like using this particular technique. So horn antennas were used and RCS was calculated for the human body. Then different modulation, demodulation architectures to extract the signals from the received signals. So direct down convergent demodulation architecture, quadrature demodulation architecture, and double down convergent architecture. So we have seen that in all three cases, we could detect both the heartbeat as well as the respiration signals. Then using VNA, the measurement setup was done at two frequencies, 2.45 gigahertz and 10 gigahertz, and signals were obtained. So signals were converted to normalized spectrum using normal FFT, and we could see that under different breathing conditions, normal breathing, fast breathing, very fast breathing, we could detect the signals at various frequencies. And through the wall estimation was done. Again, as we can now correlate with the loss modeling of various materials. So through the wall, losses were not very high. So as a result, we can detect through the wall signal as well at 2.4 gigahertz. So this was shown. At 10 gigahertz also, you can do the same thing, and you can detect the signal even through the wall. Then using direct down convergence method and Hilbert transform, the respiration signals for various cases were detected through the wall detection, single object, like multiple objects, objects at an angle, right? So the angle, the human subject is rotating, so we could detect under that condition as well. Then there were multiple human subjects, right, breathing in various rates, fast breathing, very fast breathing, slow breathing, normal breathing. So under these conditions as well, the signs were, we were able to detect the respiration signals. Then using signal decomposition, also we could detect, and then finally the the target direction of arrival and range. So this was done using receiver arrays. So this was done using microstrip arrays of 4 antennas, that's shown here. So we could detect the angles at which multiple of subjects are there, and we could detect their respiration signals as well. So angles were also we were able to detect. The range was also estimated. The accuracy was not very high in the range estimation. However, the angles were detected for the two subjects, right? Like in the three graphs that show here, the two subjects are at different angles, and we could detect the angles quite nicely using an array. And then loss modeling for different materials was done. And it was seen that the losses are not very high. The losses are not very high for different materials, and this loss modeling can further be used for improving the accuracy of the respiration signal detection. So this is all I have to present, and I'll be happy to take more questions on this. I'm sorry it got finished quite early, slightly early, but we can have a couple of questions and have interaction so that it is useful. Give me a second.
Participants, if they have questions, please they can ask the questions. Any questions from the participants? Please unmute yourself and ask the questions.
I hope I was able to deliver some content, right? So you can appreciate the work that is done, and it has a lot of practical applications as well.
Sir, there is one question. Let me read
Yeah.
it. I don't know. Grace, sir, I asked one question in chat box.
There's one question I see.
Grace, sir, is there?
Sir, for respiration, what sensor is used? That is the question. Yeah, so this question is asked by Grace Prince, and he's asking what for respiration, what sensor is used. So we don't put any sensor on the human body. There are two antennas. One is the transmitting antenna and the receiving antenna. So basically, the receiving antenna is a sensor. The reflected signal from the human body is detected, and from that detected signal, we extract the respiration signal. So there is no separate sensor as such. There are antennas which are used as you can call them as sensors. Those are used. So in the second part of the talk, like the next talk, they will be more focused on antennas, right, which are used as basically sensors to detect the signal and then transmit it further. So does that answer your question, Grace? Then another question is, actually, this is not a question.
I think no other question is there in the chat box. So any participants have the questions, please ask it. Okay, sir. Sir, can we close the session here? Can we break for a lunch?
Yeah, we can break for lunch, and maybe we can come back maybe around sorry, it is not 12:35.
1:30?
Yeah, 1:30 should be.
Okay. Thank you, sir. Thank you for your session. And thanks to all the participants for patience listening. So now closing the session 1. Now we will be here for 1 hour. Like it's like 12:35 is there. As sir is having one meeting at 3 o'clock. So our next session we will start at 1:30 sharp. So I request all the participants to rejoin at 1:30 with the same link. Thank you.
Okay, thank you.
I want to close the session here.
I will see you at 1:30. Thank you.
Thank you, sir. Yes, madam.